So I'm going to describe the variance reduction algorithm based on dimension reduction. So I'll start with an introduction, then I'll describe the algorithm, and I'll give applications to Markov chains. Then I'll give some numerical experiments, and I'll end with a conclusion. So, the goal of the algorithm is to estimate efficiently the expected value of f of u. So here u is a vector of d independent random variables u1 up to ud, and f is a function of d variables, and we assume that f does not depend equally on all its arguments. So some of the arguments of f are more important than others. So some of the UIs are more important than others. So let's start with a simple example. So we have a GTD1Q, and we have AI customers that arrive at time step I for I between 0 and D. We assume that the arrivals are independent, and that we assume that the service times are equal to 1. And we assume that the system is empty at 0, and there are no arrivals at time 0. And we are interested in estimating the expected value of the number of customers in the queue at time step D. So if xi is the number of customers in the queue at time step I, then xi satisfies the simple recursion and it's a Markov chain. And we want to calculate the expected value of x of d. Okay, so here x of d is a function of the arrivals. So the arrivals are independent. So x of d depends on the arrivals at time step 1 up to time step d, which are independent random variables. And x of d depends mainly on the last arrivals. So the last arrivals are more important than the first arrivals. Okay. And there are other situations where we want to calculate the expected value of g of xd, where x1 up to xd is a Markov chain, and g is a real valued random g is a real valued function. So for example, we want to calculate the probability that the volatility exceeds a certain threshold in 2 years from now, for instance. So if you assume that the volatility follows the Gauge model, so then the volatility is a Markov chain, and we want to calculate the probability that the volatility in 2 years exceeds a certain threshold. Also in communication networks, for example, we want to calculate the probability that the waiting time exceeds a certain amount at noon, for instance. Also, if you have a call center that closes at 5, maybe you want to calculate the expected value of the queue length at 5 p.m. Okay, so in all these examples, some variables are more important than others. For example, in the Gauge volatility model, the volatility depends mainly on the last returns rather than the returns today. In communication networks, the waiting time depends mainly on the last arrivals and so forth. So let me give a quick overview of the algorithm, and then I'll describe it in more detail. So in standard Monte Carlo, we calculate the expected value of f of u by simulating n independent copies of u, and then we take the average of f over the n copies. So in our algorithm, I simulate a random subset of the arguments of f at each iteration. So I change only certain arguments of f, and then I reuse the remaining arguments from the previous iteration. Okay. So let me give a quick overview of the results. So in standard Monte Carlo, the expected running time needed to achieve variance epsilon square is typically of order d multiplied by epsilon to the power minus 2. Because in order to achieve a variance of epsilon square, we need to simulate epsilon to the power minus 2 copies of u. And typically the running time to simulate a copy of u is of order d. So the total running time is typically of order d to the multiplied by epsilon to the power minus 2. And in our algorithm, under certain conditions, we can estimate the expected value of f of u with variance epsilon square in time d plus epsilon to the power minus 2. Okay. So if epsilon is small enough, basically we have a variance reduction of order d. So there were previous methods that that rely on the fact that certain variables are more important than others. So there are other variance reduction methods such as the splitting method, the quasi-Monte Carlo algorithm, and the multi-level Monte Carlo methods that use the fact that certain variables are more important than others. So let me now describe the algorithm in more detail. So let us assume that the importance of ui decreases with I. So this means that u1 is typically more important than u2, which is typically more important than u3, and so forth. And let us define the set A of vectors in R, so of dimension d, so of d-dimensional vectors, q0 up to qd minus 1, such that q0 equal to 1 and q is a decreasing sequence. Now, if q is a vector that belongs to A, let us define a sequence nk of independent integers that belong to the interval 1 to d, and such that the probability that nk is greater than I is equal to qi. So nk for any k greater than or equal to 1 is a random variable, is a random integer that belongs to the interval 1 to d, and the probability that nk is greater than I is equal to qi for I between 0 and d minus 1. Okay, so the algorithm simulates n copies of u. So v1 up to vn are copies of u. They have the same distribution of u as u. So v1 is just simulated. So v1 is can be simulated like u. And now for iteration k, where k is between 1 and n minus 1, we calculate vk plus 1 from vk by changing the first nk components of vk, and we keep the remaining components unchanged. So here we draw nk. Nk is a random variable, and we change only the first nk components of vk to calculate vk plus 1. Okay, as the remaining d minus nk components remain the same. And then we output fn. Fn is the average of f over the vectors v1 up to vn. Okay, so this is the algorithm. Okay, and now let us analyze the algorithm. So for I between 1 and d, let ti be the expected time to generate vk plus 1 and calculate f at vk plus 1 when nk is equal to I. So when we want to change only the first I components, let us denote by ti the expected time we need to do this. The expected time we need to change the first I components and to calculate f on the resulting vector. Okay, so then it's not hard to show that the expected running time of any iteration in the loop is given by this equation. So the expected running time of any iteration is equal to t, which is the sum for I equal to 0 to d minus 1 of qi multiplied by ti plus 1 minus ti. Okay, and now the expected running time of the first n iterations is equal to n minus 1 multiplied by t plus t sub d. Okay, because the running time of the first iteration is t sub d, because we need to simulate the entire vector u in the first iteration, and then in the remaining n minus 1 iterations, the expected running time is equal to t. So the expected total running time of the first n iterations is n minus 1 multiplied by t plus t sub d. Okay, so now let us analyze the variance of Fn. So first we need to introduce Ci. So Ci is a quantity that measures the importance of the variables ui plus 1 up to ud. So formally Ci, where I belongs between 0 and t, where I varies between 0 and t, Ci is equal to the variance of the expected value of f of u conditional on ui plus 1 up to ud. So Ci is the variance captured by by the last d minus I components of u. So C0 actually is equal to the variance of f of u. CD is equal to 0, and if ui plus 1 up to ud are not important, then Ci should be small. Why? Because if ui plus 1 up to ud are not important, then the conditional expected value of f of u given ui plus 1 up to ud, this conditional expected value should be almost a constant, and so the variance Ci should be small in this case. So Ci measures in some way the importance of the last d minus I components of u. And we can show that the sequence Ci is a decreasing sequence, and also actually Ci can be calculated by Monte Carlo simulation. So it's equal to the covariance of f of u and f applied to another vector where we change only the first I components of u. Okay, so we can calculate Ci. Good. And actually Fn is an unbiased estimator of the expected value of f of u, because actually Vk has the same distribution of u. So each of the vectors Vk that we have simulated by our algorithm has the same distribution as u, and so the expected value of f of Vk is equal to the expected value of f of u, and so this implies that the expected value of f of n is exactly equal to the expected value of f of u. Okay, since f of n, I remind you that f of n is the average of f over v1, v2, etc. up to vn. Okay, so Fn is an unbiased estimator of expected value of f of u, and this theorem gives the variance, an upper bound on the variance of Fn. So n multiplied by the variance of Fn is upper bounded by this quantity, where Qi are used to generate the sequence Nk, and the new stars essentially are equal to the Ci's. Okay, so we have this inequality, and this inequality is actually optimal, because as n goes to infinity, the left-hand side goes to the right-hand side of this inequality. So this inequality is optimal. Okay, so now we have the expected running time and we have the variance, and so we can calculate the expected running time multiplied by the variance. So Tn multiplied by the variance of Fn, and so we can show that as n goes to infinity, the expected running time multiplied by the variance is given by this function R of Q and mu star, where this is R of Q and mu. So R of Q and mu is a product of two quantities. The first one is essentially the expected running time up to a constant, and the second quantity is essentially the variance of Fn up to a constant if you replace mu by mu star. Okay, so we have the expected running time multiplied by the variance, and so if we let t total Q of epsilon be the expected time needed to guarantee that the statistical error is at most epsilon, then we can show that this expected running time is at most equal to Td plus the time variance product multiplied by epsilon to the power minus 2. Okay, so in order to get precision epsilon, the running time that we need is at most Td plus the time variance product R of Q and mu star multiplied by epsilon to the power minus 2. Okay, and now how do we get an upper bound on the variance? So we have an expression for the variance that depends on the CIs, and in order to get an upper bound on the variance, we need to get an upper bound on the CIs, and we have a proposition that allows us to get an upper bound on the CIs. So this proposition says that if we can approximate f of u by a function of the first I components, so if you have any function of the first I components that approximates well f of u, then Ci is small. Okay, so we have this inequality. Ci is upper bounded by the variance of f of u minus a function of the first I components of u. Okay, so now let's give a simple example. So we have u1 up to ud, so they are independent real random variables, and the standard deviation of ui is equal to sigma I. We assume that the sigma i's are in decreasing sequence, and let f of x1 up to xd be a certain function of the sum of the x's. Okay, so here g is a one Lipschitz function, so it's a real valued one Lipschitz function, and f of the vector x1 up to xd is equal to g of the sum of the x's. Okay, so you can check in this case that ti is at most equal to ci for some constant c. So if we the time we need to change the first I variables and to recompute f is at most proportional to I. Okay, and now we are going to get to show an upper bound on the Ci. Actually, we can approximate if we consider this function fi of x1 up to xi is given by this equation. Then we can show using the previous proposition that Ci is upper bounded by the sum from j equal to I plus 1 to d of sigma j squared. Okay, so using the Lipschitz property, we can show this upper bound on the CIs. And now if we set Qi equal to sigma I plus 1 divided by sigma 1, then the time variance product is upper bounded by this quantity. So it's upper bounded by a constant multiplied by the square of the sum of the sigma i's. Okay, so in particular, if sigma I decreases quickly with I, so if sigma I is big O of I to the power gamma with gamma less than minus 1, then the time variance product is upper bounded by a constant. And so the time needed to achieve precision epsilon in this case is at most big O of d plus epsilon to the power minus 2. Okay, because the time variance product is upper bounded by a constant. So here we have used this equation. So here the time variance product is upper bounded by a constant, and from this equation we find that the time to get precision epsilon is at most d plus epsilon to the power minus 2. In general, if Ci is upper bounded by I plus 1 to the power gamma, where gamma is less than minus 1, and if Ti is proportional to I, then we have the same result. So the time variance product is upper bounded by a constant, and so the time to achieve precision epsilon is big O of d plus epsilon to the power minus 2. Okay, so let me describe the applications of to Markov chains. So we have a Markov chain xm where m varies between 0 and d. And we assume that the Markov chain is driven by variables yi. So xi plus 1 is some function of xi and of the random variables yi. And so here yi are independent random variables. So for example, in the application, in the first example on queues, yi's represent the arrivals at each time step. Okay. And so we want to estimate a certain function of the state of the chain at time step d. So we have some function g, and we want to estimate the expected value of g of x of d. So here we are going, in many cases, the most important variables here, in many cases, are the last yi's. So the last yi's are often the most important random variables in this case. And so in order to apply our algorithm, so we are going to use a time reversal. So we set ui equal to y of d minus I. And so in this case, the most important variables are the first ui's, okay, which correspond to the last yi's. Okay, and in this case, you can show that g of x of d is a deterministic function of u1 up to ud. Where the ui's are, the first ui's are the most important ones. And there is a simple expression for Ci in this case. And using the analysis in the book of Asmussen and Glynn, the analysis suggests that Ci decreases exponentially with I for a variety of Markov chains. So we can apply our results. So, we have some examples. In the paper we apply this result to the Garch model, and we show that the Ci's are exponentially decreasing with I, and so the running time to achieve precision epsilon. So if you want to calculate the probability that the variance exceeds some threshold at time step d, the running time to do this is big O of d plus epsilon to the power minus 2. Okay, and also in several queues, also we can show that under certain conditions the Ci's are exponentially decreasing with I, and so the time to achieve precision epsilon is big O of d plus epsilon to the power minus 2. Okay, so here we have some numerical examples. So we have an example on the Garch model. We want to calculate the probability that the variance exceeds some threshold at time step d. And so I plot the variance reduction factor in terms of d. So as d increases, we see that the variance reduction factor for the randomized dimension reduction algorithm increases. The variance reduction factor increases, and it is essentially proportional to the dimension d. And also we have a multi-level Monte Carlo algorithm also that achieves variance reduction in this case, but our algorithm has better properties than the multi-level Monte Carlo algorithm in this example. So we have other examples on queues in the paper. Here again, so the variance reduction factor increases with d. So in this example, the variance reduction factor is about d divided by 100. Okay, these are other examples. So that you can find in the paper. So as a conclusion, We have a randomized dimension reduction algorithm that estimates the expected value of f of u, assuming that f does not depend equally on all its arguments. So some arguments are more important than others. And under certain conditions to achieve precision epsilon, our algorithm requires big O of d plus epsilon to the power minus 2 computations, as opposed to big O of d multiplied by epsilon to the power minus 2 under the standard Monte Carlo method. And our algorithm can be used to calculate the expected value of a function of the state of a Markov chain at time step d for certain Markov chains. And we have our numerical experiments confirm that our method highly outperforms the standard Monte Carlo method for large values of d, and shows that it's high resiliency to discontinuities. Okay, so the paper actually has appeared already in Management Science, so you can find it here in Management Science. Thank you.